Good afternoon. Thanks for coming. I'm Arun Subramanian. I lead the data science and analytics team at Baker Hughes, a GE company. We'll talk today about how we deal with analytics at scale for the industrial world, specifically for oil and gas, but more in general, what are the scalable aspects and what are the commonalities of analytics in the industrial world, right? And just to give you a little bit of an introduction of the kinds of problems that we're interested in. And by we, I mean the larger GE, so this is the largest GE company. So for those of you who don't know, every 2 seconds, an airplane takes off somewhere in the world with a GE engine on it. About 30% of the world's power is generated by a GE turbine of one kind or the other. Right. And we formed Baker Hughes, a GE company, last July by merging GE Oil and Gas with Baker Hughes, two companies which by their own merits were large giants in their own merits. But the merger brought together the world's first full-stream oil and gas company. By that we mean the first company in the world that can do exploration for oil, extract oil, ship the oil, refine it, and then do something with the refined products. Right? So make energy, make something else with the products. The first company in the world that can do that at scale. Now, to do any of these individual things by itself is a big feat. Doing all of these things simultaneously in one company requires us to build a lot of models repeatedly. And I've not even touched upon what we do in the healthcare space or in the transportation space, for example. These are just simple examples. And to do this at scale, daily, we have to build thousands of models. And for us, models are any representations that connect a set of inputs to a set of outputs. Now, that can be as simple as a simple equation or a full-blown partial differential equation that takes about 2 months to solve on the world's fastest supercomputer. Right? All of those things for us is a model. Now, to do this effectively, we of course need the raw material for it, which is data. And we deal with data in two ways. So we have what we call two big dichotomies of silos. The first silo is data. The second silo is analytics, or second silo is subject matter expertise. I'll first tackle the data silos. And if you look at across the entire industrial spectrum, the first one, of course, is oil and gas here listed. From there to aviation, say take an aircraft that takes off from New York, lands in London. The aircraft was designed about 20 years ago. The engines are not collecting that much data. That's roughly about a terabyte of data generated. Right? Not much of it is stored, not much of it is analyzed. But today's newest aircraft generate about a terabyte per hour of flight. Right? Take that in the oil and gas world, where an offshore oil rig for the past 30 years has been generating roughly 15 to 20,000 tags worth of data every 2 seconds. And almost all of it has been stored. Right? Compared to the power or transportation or the aviation industry, the oil and gas industry has at least a couple of orders of magnitude more in terms of data, primarily because they had to deal with uncertainty from the get-go. There's very little you know about the reservoir. There's very little you can actually model or control about what happens subsurface. Whereas an engine, it's complex, it's extraordinarily sophisticated, but you control almost everything around that particular field. So the uncertainties exist, but they're far smaller. So the data sets that you see in the oil and gas world significantly outstrip anything else in the industrial world. But if you compare that to any data sets in the ERP systems, traditional ERP world for the last 20 years or last 30 years, where you think about any transactional data sets, any kind of maintenance records, any kind of information that you've been sharing and storing and retrieving in the traditional enterprise world, gets dwarfed by the industrial data set by at least 2 to 5 orders of magnitude, both in terms of volumes and velocities. Right? And there are no systems that have been developed that would tackle something at that scale. Even the modern industrial or the Internet 2.0 kind of technologies, where we track everything that everybody is doing in this room, everybody that's doing anywhere in the world, where they are, where they're going, what they're probably going to do, it still gets dwarfed significantly. And I'll give you some examples of how we go about solving it. But this is just one side of the story. Right? The data silo is one side of the story that everybody talks about. The other side of the story is the analytics silo, or the subject matter expert silos. where people have been building analytics for decades. People have been building analytics for 50 years. Right? If we have the luxury of going and building a model from scratch, from a data set that you still have to prepare painstakingly, that's a great thing. You have a lot of frameworks out there today to go build. But if you had models that have been in production for decades, that people understood, have been using it in production, today folks who are using it may not necessarily understand all the nuances of the model. You don't necessarily want to go touch it. You don't necessarily want to go tweak it or change it. You want to be careful about it. The same thing in the financial world, where you really don't want to go change the financial metrics without understanding what went on for 20 years internally. Right? Very, very similar things here. The only difference is the consequences of doing something wrong can be catastrophic. Imagine we have to decide, based on a model's prediction, whether I have to shut down an offshore oil rig, which is producing about 2 million barrels a day. I have to predict whether a particular engine on a particular aircraft needs to be pulled for maintenance before this takeoff, or is it okay to leave the airport today? Right? Consequences of a wrong decision are catastrophic, and false negatives are really not okay. So there are no models that we generally tend to build where false negatives are okay. Our false positive rates are, that's why, generally high. Roughly around 20 to 30% would be okay for a model in the industrial world. But a false negative rate, meaning the risk of me saying something is okay when it's really not okay, has to be zero, or as close to zero as possible. Right? And that's where the consequences come in. And analytics silos exist because of that, because it takes a lot of expertise for somebody to build and maintain these models. Now, for us to come in and scale this, if I have to democratize analytics for 5,000 engineers in a company like Baker Hughes, for example, I can't necessarily go in and say, drop everything you're doing. Here's the brand new framework. Go build all your models with the brand new framework. Some would, but most of them would still go back to Excel spreadsheets and, in some cases, their Fortran code. Because that's what works, and they know it works. Right? So we need to somehow bridge these silos together, both the data silos and the analytics silos. And fundamentally getting a federated orchestration engine where you have a lot of these models talking to each other, not necessarily independent islands, but actually models that talk to each other, is fundamental if you want to scale analytics in the industrial world. But I'll show you some examples of that. But the example that you see here, where there is a Python model that gives an output that gets fed into a Fortran 77 model, which we can only probably run as a black box, that then talks to a model that's written in Go, that then talks to a model that's written in C. It's a daily reality for us. It's not an esoteric example. In fact, there are very, very few examples where we had to build a model that gets you to an outcome that's just written in one framework. Okay. Now, I've listed some of these things. Some of these things could be provocative. Some of these things you could say myths or reality, depending on your point of view and what your experiences have been. But we've heard all of these things, and we talk to customers on a daily basis. And irrespective of where they are in their journey for digitalization, where they are in their journey for moving to the cloud or not, whether they believe in AI or whether they think it's a myth, a lot of these things are what customers tell us daily. Now, there is some truth to a lot of these statements, but they hide the bigger truth, right? So, for example, one of my favorites is when people say neural networks are old news. The general statement is, I've done this in the 90s when I was doing my master's. They're really bad. They got to about 60% accuracy. They really never got anything meaningful in engineering parlance, so we moved on. What's so new about all these new neural networks that are coming out? And the other thing I didn't list here was people telling, oh, I've done deep learning 20 years ago. And for those of you who do deep learning here, that's really a silly statement. Right? And but the reason why people walk around with these myths is because they haven't gotten the outcomes that everybody seems to be promising with analytics. And by the way, the analytics promise has been the same for the last 25 years. There used to be the digital well of the future, and that actually came out in the late 80s and early 90s, where they wanted to go censor up the entire oil field and say this is going to create a huge revolution. That's like me coming and telling you email is going to make you more productive. Okay. So it just has to be balanced with what and how you're actually applying things to. And just to bring home the point, I want to to walk you through a few examples. And one of the favorite things, and just full disclosure, right? So my background is through and through aerospace engineering. I grew up in the physics world. We did data science as a necessity. We got into doing large-scale data science because physics alone was not sufficient. But the general pushback from most subject matter experts is the world has been run by physics. We understand it. That's the only thing that can solve all kinds of complicated problems, right? So if you were to predict purely from data where a particular stone would land if you throw it, and you don't know anything about gravity, the only thing you need to go by is observations of each of the stones that are being thrown. If you have to only purely build that model, this is how it looks like. So the projectile is going. We don't know anything more than saying it's just a linear projection. If this is the first time I'm observing, it takes me more than 10,000 observations to track that the stone is even going to come down. I don't know anything about gravity, right? And even the simplest model, the most sophisticated model you can build, requires a lot of observations. On the flip side, if you're a high school student and you're given the same problem, stopped working. There you go. You'll tell me that all the data you need is just one data point. All you need is the velocity, the speed, and the angle at which you threw the stone at. Anywhere in the universe where there is gravity, you can predict precisely where the stone will land, right? Even middle school physics would tell you that. The problem really is reality. If I didn't know exactly what angle I threw the stone at, I just add a 1% uncertainty in the initial angle, my output changes by about 20%. If I add a 5% uncertainty in wind speed, all of a sudden you have 100% uncertainty in where the stone will land. And this is the simplest physics problem you can tackle. It's just one variable and just very, very little uncertainties. Imagine if you have to go predict whether a particular engine is going to have a fault, or I have to shut down an offshore oil rig. Massive problem, thousands of variables, lots of uncertainties, lots of things you don't know. You still have to make a decision. So physics alone can get us astray significantly. In fact, in this problem, if we add a few more uncertainties, it'll tell you that the stone is flying backwards. Right? So we have to be very careful with that. Right? And the other thing that people generally don't like to talk about is the fact that, yes, data is cool, it's everywhere, everybody likes to use it, but the reality is not much of it is useful. So this is a real use case where the data set is from an actual asset. Think of this as a very large-scale asset. It could be a jet engine, it could be a gas turbine, it could be any of those kinds of things. We are the equipment manufacturer, we meaning GE and BHGE. We have all of the data sets about how it was operated. So the top left gives you the operating condition, one of the variables that are being measured for the entirety of this particular asset's life. The actual data there is in blue dots. Everything else there is what we estimated or generated through other sources. The reason we had to do that was because here in our databases, systems of record, it says the asset started operating in 2001. Right? That's their operating condition. But the asset actually started operating in 1994. And there's lots of things that happened to it before our systems of record actually caught up. Right? And if I had to go predict anything about the system, and I say I only go by the blue dots, it doesn't matter how sophisticated my techniques are, how sophisticated my data scientists are, or even the physics-based modelers are, my models would still be wrong. Because data is only about 60% correct. Right? So we had to go correct for it. And while we started digging into this over the last decade or so, we realized it's not just missing data is all not made equal. We actually had to go invent different ways of categorizing missing data. So you have, that's why you have partially missing 1, 2, fully missing 1, 2, 3, and things like that. And each one has to be estimated using different techniques. So imagine the data scale we started with, that includes the missing data. If we add on the augmentation activity that goes on to add the missing data back in, that problem becomes 2 or 3 times worse in terms of volumes. Right? Because the minute you go add data in, and if I change the color coding to all be just blue, it'll be very hard for you to tell which was estimated and which was real. then you have to figure out which models would use which version of the data sets that you're using, and how do you keep them all in sync. That becomes a massive problem as well. And just to show you the quality of how well we can actually estimate, the top right figure, blue histogram, tells you the actual data set. So the mean is around 559 with a standard deviation of about 33. The estimated values are very, very close. It's 560 versus 31. Right? So it's very hard for someone to tell after a while whether the data set was real or not if you didn't properly tag them. And this happens regularly. Right? This happens on an engineer's desk where they have to change something in the data set, passed on the data set to somebody else. They built a model that had a significant consequence and they pass it on. And there's no systems of record for any of those. Right? And that becomes the actual data of record as well moving forward. Right? So really quickly, industrial analytics for us is a combination of three things. People have been doing analytics for a long time, combining domain knowledge with standard software techniques. Right? The new kids on the block are a new way of doing data science, mainly deep learning based data science, and new way of building software on the cloud, microservices, self-scalable. Right? The traditional solutions are a combination of domain knowledge with software. I would say finding very, very hard problems or finding solutions to hard problems like finding a needle in a haystack is a combination of modern data science with modern software. Predicting what I'm going to buy before I actually go and buy it, hard problem. Predicting how long it'll take me to go home before I actually tell you when I'm going to go home, again, a hard problem. In a large cases, it's been solved. Right? A lot of cases, it's already happening today. The case in point for industrial analytics is really a combination of all three things, because it's not even finding a needle in a haystack, it's finding a needle in an ocean of data. Because most of the times, the one thing that you're trying to go predict, you don't have any data for. So if you're trying to predict, for example, when would a bearing fail, you would have hundreds of sensors on a gas turbine, but you don't have a sensor on a bearing that's about to fail. Many times, the sensors that you have are all confounded and not necessarily calibrated in the last 20 years. So how exactly do you make sense of it to predict something that you're going to go predict without understanding the sensors around that particular piece? That's really the problem that the industrial world faces. And that is not just one esoteric problem, not just one problem here or there. Almost every problem of value is a combination of all three things. Right? And we got here not as an epiphany moment where we just sat there and said, this is the hardest problem we need to solve. These are the problems we have to solve every day. These are the problems our customers have to solve every day. If we could solve it with traditional techniques, we would. If we could solve it just purely with data science, we would, because that's the easiest thing to do. Because there are a lot of techniques out there are a lot of systems out there that will let you go do that. The reason we had to go combine all three things painstakingly is because that's the only thing that actually gets us to a solution that's meaningful. Right? Now, we talk about digital twins a lot, and the world talks about digital twins a lot today to the extent that it's almost an abused term. For us, digital twins are very special. We get there because we can't solve these problems with any of these individual techniques by themselves. And the way we define it is it's a digital representation of a physical system or an asset or a process that has a few characteristics. It has to be live, it has to be continuously updatable, and it has to be adaptable and scalable all at the same time. Now imagine I have to do something specific, or I have to make something specific and scalable at the same time, meaning I go build a model of a particular asset or a particular system. I make it so specific that it's specific to that particular system. It doesn't scale by definition. So how do you go build something that's both specific and scalable? Even worse, I made it specific, okay, I can somehow make it scalable. I now have to go make it adaptable, meaning if I go change something in the physical system, I change a pump out, I change a compressor out, I should be able to change only that portion of my entire digital twin and make the whole thing work again. I don't have to go back and rebuild the whole thing. Right? Those are very, very hard things to do, and the reason we had to go do it is because we have to run digital twins thousands of times a day for every single implementation we have out there. So it's hundreds of thousands of digital twins running thousands of times a day. So we can't really run these at scale if we have to go do these things manually. Typically how these things are done, you get a team of 6 to 10 PhDs with some designers who are experts in the system, let them loose for about 6 months, and then they come up with one model that's specific but non-scalable and non-adaptable. Right? And the reason why we had to go mix all these three things together, so we always start with physics, that's physics-based, so that we can actually build on top of it, where physics allows us to do known knowns. So if you know something is going to be a problem, physics will get you to a precise solution very quickly. Probabilistics, because that's where we started with, without uncertainties, I really cannot predict the real world, right? Deep learning allows us to really sleep reasonably well at night because it allows us to go and deploy these systems to watch for things that I know are going to go wrong, but I don't know what they are. So I know something is going to go wrong. That's all I know. I don't know where, I don't know when. So those systems allow us to go watch and adapt the models for that, right? So I'll give you a few examples of that, right? I'll make it a little concrete for you for what a digital twin is. Take if somebody comes and tells you they have a digital twin of a well. And in this particular case, this is a well with an artificial lift system. Think of that as a pump. It's an electric submersible pump that's about 2 miles deep under the earth. When we say it's a digital twin of a well, we connect a reservoir model, that's the IPR curve, to a pipe model, to a pump model, to a tubing model that finally gets you a pressure differential at the end. And what you're trying to predict is how do I change the operating conditions of the pump and the well to make sure that I produce as much as possible without damaging anything, both the well as well as the pump. Right? And to do this, roughly one digital twin has about 8 models running in sequence along with an iterative loop internally. So it's not just a linear sequence. Right? And this we would consider a fairly moderate level complexity digital twin. Right? Now the way we use it is an operator would go in and say, okay, how do I improve my production from my set of wells? To answer that question on one well, I typically have to run a digital twin at least a few thousand times. And to get a plot like this, where I have a plot of power versus total liquid flow from that particular well by changing all the parameters, all the gray dots, each one of those gray dots is a prediction or an inference through the digital twin. The best family of solutions are on the blue dots. The problem is today I might be operating on the black diamond. Without knowing what my space looks like, I might just randomly increase power and hit any one of those red dots on the top, where I increase power, meaning I'm spending more, and I'm actually producing less. That happens a lot, where intuitively you can go tweak some things. You really don't know where you are in your design space. In this case, it's a fairly simple problem. We're only changing about 6 parameters. But if you're in an oil field, there are a few hundred wells, you're automatically going into a few thousand parameter optimization problem very quickly. And that needs to happen a couple of times a day. But today, the best you can do with the tools out there, not just in oil and gas, but in aviation and power and any one of these industries, is to run an optimization like this, not even a global optimizer, but a local optimizer. It can take anywhere from 20 minutes to about 2 hours for an advanced engineer to go run it. Right? So we took this as an experiment. And about summer of last year, we went and built the digital twin for a single well. It took about 3 minutes per well. We scaled it with the techniques we talked about up to now, combine physics, data science, and software scalable on the cloud. In about 6 months, we got a 1000x improvement, going from a single well optimization that took about 3 minutes to run to a cluster of wells where about 20 wells were there in a cluster. You can optimize it in about 30 seconds. Right? The reason why you get a 1000x improvement is because it's not a one-shot optimization. It's a game of whack-a-mole. So you go do something else in one well, something else goes wrong in another well. So you fix it, go somewhere else, change something else goes wrong. So you do that iteratively multiple times. In fact, to get to that solution, you need to run the model about 20,000 times to get to that answer. That's really where you're getting the 1000x improvement. But we wanted to push it one level higher, saying, okay, we keep the models the same, we scale the software. We push it to the cloud. We actually orchestrate all these models to run on the cloud and see what actually can be done at a field level optimization. The solution doesn't exist today. And to be honest, none of our customers even asked us for it. In fact, when we go and presented the 20 well optimization, the response was, this is great. Today we do that once every 6 months. This one might let us do it once every 2 weeks. Right? And the field level optimization, the response was, we really did not know that this is even possible. And the response was actually opposite. They came back and said, can you do 5,000 wells? Can you do 9,000 wells simultaneously? Right? Because the pace at which this is moving, The 6 months deadline was just because we had our internal conferences. We actually had it scaled in about 3 months. Right? I'll show you how we walked through that. And in just a year, for an engineer to go from maybe doing a single well optimization every 6 months to doing a field level optimization a couple of times a day is a phenomenal improvement. Right? Okay. And the notion of using deep learning in traditional industries like oil and gas or aviation or power, but they're very risk averse. Right? They don't really want to trust a model by itself. So here's some of the things that people generally talk about anomaly detection, but the things that resonate with industrial customers is people don't really want to go set rules. Most of anomaly detection systems out there want to tell you to come and say, here is my threshold for a set of variables, set my thresholds, and after that I'll go tell you when something is going to go wrong. And this has to be done a priori before it goes and catches things. So the biggest promise of automated anomaly detection with deep learning primarily is you can actually catch anomalies without necessarily knowing what these anomalies are beforehand. I don't have to train for anomalies, I don't have to train rules. In fact, I don't even need to tell it what are the sets of inputs I need to be looking at. As long as you have a data stream coming in, and as long as you knew what the normal state was, I can go say what was abnormal. Right? That was the first foray for us into deep learning. But from there, we actually went into deploying a live application for a customer, where the customer was recording about 10,000 sensors off an offshore oil rig. Actually, this was done by the customer who actually already pushed the data to Google Cloud. All we had to do was train with a 6-month data set they had, which was normal, with no abnormalities. And within about a 6-week period from starting from scratch, going from not knowing what the data is, not even knowing what the asset was, to having an anomaly detection working in an application roughly took us about 6 weeks. Right? And this particular application that you see here, this failure mode that was caught, that's shown in the top right, where it's just an anomaly score as a combination of about 16 different sensors. We caught an anomaly. Then the next immediate question is, okay, this is something going wrong, but is this just a blip, or can you tell me what is causing this problem? That's the plot on the bottom right, and I'm not sure if it's showing up properly here, but the colors actually indicate as a function of time which variables are actually affecting the anomaly score. So you can actually start going and figuring out what is causing the anomaly. That's the next step. The step after that is actually figuring out what is the actual cause, what is the root cause actually, right? And to do that, you actually train with maintenance logs along with this time series data sets as well. So this is actually an autoencoder running for a set of about 24 different variables over a period of 2 years. Built, running, live on GCP in about 6 weeks. Right. The other kind of systems that are actually fairly effective for using in deep learning is image recognition kind of use cases, right? So this is a use case where if you've driven from here to LA, you would have seen a lot of these pumps. These are called rod lift pumps. And the biggest problem with rod lift pumps are they fail quite often. And the failure modes generally are categorized using these images, which is a plot of the force versus displacement of the rod that keeps going in and out, right? And depending on how that shape looks, an experienced engineer can say what is the actual failure mode. The problem is 2 failure modes look more or less the same. Right? So it depends on who you ask and when you ask in terms of finding out what exactly is the failure mode until you actually have to stop operations and then pull it back up. Right? And worse, if you use traditional techniques to do distance-based metrics, to say this is the overall graph, tell me what this new graph looks like and what is it closest to, you get to an accuracy of about 60%. Right? So we took the latest just an image object recognition model, augmented it using transfer learning with just the failure mode images that we had, and let it loose. So if I run this demo for you, you can see most of the detections where on the left-hand side is the data set that's coming in for a particular pump, for a particular rod lift pump. On the right-hand side is what the model is predicting real time. So this is a deep learning model built and deployed for inference in this particular case, the times are actually running on an edge device with a small Jetson with the timing that we are actually running. Right. So you can see instantly it is catching with under 1 second delay what the actual failure mode is. And this model was really not that optimized yet. We just took the standard model that was published, augmented it with the data sets we had, and the accuracy went from about 65% to 93%. Right? And the data sets were not even that high. So it was only a few hundred failure modes. Right? And if you optimize the models, you can get up to about 93% to about 97%. The last 3% is something that you have to go collect more data for. Right? So these are some of the examples that we are building and deploying in the field, both with just traditional deep learning, augmenting with deep learning. Right? The other kind of deep learning models that we're building quite effectively are the knowledge systems. And the request for this one came from a couple of customers where the request was, we have a lot of documents that we have generated over the last 30 to 50 years. We have a lot of training material that we generally use for our new recruits to be trained on our operations and to make sure that we can actually get them up to speed very quickly with our subject matter experts. What most of the industries are facing today are a dichotomy of problems. The first problem is they're losing a significant portion of their experienced workforce in the next 5 to 10 years. Right? On the other side, the new workforce that's coming in are used to learning and interacting in a very, very different way. They don't necessarily want to sit through 3 weeks of training on just going through and doing one task. They want to be able to go learn, they want to be able to go search and find information as they need it. The problem is to enable that and to bridge the gap between people who are retiring and the people who are coming in. You need a knowledge system that can quickly learn and adapt. Right? So in this case, we built up the knowledge system. So we had the standard English language NLP models. We took those and we trained those models to understand technical English. So how do you go interpret tables? How do you go interpret tables and figure captions? How do you go get a natural language query to return an answer that's not a pure retrieval, but actually something that generates text? So we had to go build that. And after we built that, we realized that the corpus of data that we had to go build it had to be expanded with all the subject matter expertise we had internally in Baker Hughes GE. Right? So we made an English language speaking model understand a technical language based on all the technical language documents that are out there in the world. Then we made that model into an oil and gas person. Actually, we made that into a BHGE person because it understood our language. Then we took that model and tried to apply it to a customer and realized it was like a BHGE person talking to a person in BP or Shell. We can understand each other, but then we don't know our lingo exactly. We have our own acronyms. Right? So we had to go get the documents from the customers to augment this model as well. So just to get to a system that understands a natural language query, respond to it in the customer's context, to get to, for example, a user input going in, having a spelling correction that's oil and gas specific and customer specific, and go through and give recommendations based on what answers could be given. Because if you go and ask a general question, you can, of course, go to Google or any of the search engines and then ask a general question. You're going to get a very, very generic answer. What they really want is an answer that's specific to the person who's asking the question in the context of the company that's being asked. So to just get this one simple example working, where somebody went and tried typing in grammar. Right? So if you go try that in Google today, it'll get corrected as grammar or Grammarly or any of the many English language corrections. Right? What they actually wanted was a Gamma board or a HT Gamma Elite that is specific to that particular customer. They also wanted Grammarly and other things, but they would be ranked down, much below what a general purpose search engine would give you. Imagine extending this out where you just go start entering natural language queries and a report, an actual full-blown report gets generated for you to go train yourself for the query that you entered. That's really where the oil and gas language model is getting used. In fact, one of the models that we built with which requires significant compute is the oil and gas language model. And we continue to evolve that as we speak. And we started, of course, with English, but because we are an international company, and also the corpus of understanding about any of the industrial world is not just in English. We actually are starting to build translators from English into all kinds of other languages as well. Okay. Now, um, the other thing we wanted to talk about was democratizing analytics. Right. Now, we talked about data silos, we talked about analytics or subject matter expert silos, but there's also the other problem that we constantly come across. Hey, this is working on my laptop or on my system. I've shipped it to a DevOps or a Cloud Ops or another analytics person. Now it's your problem to run it. It just works fine on my system, right? Containers solve that significantly. But we had to upskill or up-level our analytics folks because they come not just from software or programming backgrounds, but they come from deep engineering and physics and domain expertise backgrounds. So we just did a quick check of how long it took us to onboard somebody. So usually, based on a person's background, it would take anywhere from a week to a couple of months to fully onboard somebody to be productive in building new analytics and pushing it into our production systems, right? And that was before containers, before we had CI/CD pipelines, both on the cloud, on somebody's laptop. It was more or less mirrored the same way. So it's not just about upscaling, it's also downscaling. How do you downscale your overall system so that somebody can do their work in their small ecosystem and then push it back into their overall systems as well, right? So we went from somebody taking anywhere from a week to 2 months to a couple of hours. And these were tested on a variety of people where you had a lot of expertise with containers and almost no expertise in containers. In fact, we had people who came in with absolutely no expertise in containers or programming, who still got up and running in the first day to push production code. Right. The other one was we went through painful quarterly releases. It used to be nerve-wracking sitting right before midnight because we had already promised our leadership that we're going to release today, and something that was working just fine the day before or even in the morning would break just 10 minutes before production. We've all been there. And it was painful quarterly releases to today, we can actually do continuous releases from a person who's built analytics, who does not necessarily understand the overall working mechanics of a large-scale enterprise software system, pushing something, making it into production, and actually being okay pushing it into production, right? And we can do that in some specific cases. Of course, I'm not claiming we do that on all cases. But for the capability for the analytics person to write code and the same code to be shipped to production is fundamental if we have to scale any of this. Okay. Now, I'll quickly run you through a demo. The demo I'm going to run through is trying to build a few thousand models rather quickly on GCP. And to enable this, we built almost all of our services using cloud-native Google services. And we have an internal tool that we also use as our analytics engine for all of our products for the customers called Applied AI. We are running Applied AI on GCP core services. So it's our code running, but using the GCP core services. So we are using the Kubernetes engine. We're using, say, all of the storage services that Google provides natively, including all the perimeter security, DNS, cloud DNS, and firewall rules and everything. Okay, and hopefully the demo gods are smiling on us. Let's see if this works. Okay, can we switch? Okay, perfect. So what you're going to see here, you can see we have a Kubernetes engine. We have the cluster running that's fairly large. Now, we also have both a browser-based interface that we won't be demoing today for citizen data scientists or subject matter experts to go in and build a lot of models. But we have a CLI that a more advanced person can go build a lot of models very, very quickly as well. So if I do my CLI on the left-hand side, you can see I can do a lot of things. I can log in, run a few models. I can check the status of the models. But we can also do guided build. Okay, and guided build is where I don't necessarily know much about my problem. I was given a data set by somebody. I need to go build a lot of models with that data set. I don't necessarily know what models I need to build. I don't know what techniques are going to be useful. I don't know if there is a lot of missing data in it. I'm not given much information about that data set. And that's a very standard use case as well, where somebody gets dumped with the data set and say, go do something with it, right? Or there may be an outcome, but they may not say how to get to an outcome. So about 60 to 80% of a subject matter expert's time goes into figuring out what do I do with this data set, right? So this is trying to figure out how do you reduce that 60 to 80% of your time to maybe 20 to 30%, rather than spending 80% of your time just wallowing in the dark. Okay. Now, we've already logged into the CLI, and if I go into our actual Kubernetes engine, as usual, the token has expired. Let me make sure I get my token. Give me 1 minute. Okay. So we've extended Kubernetes to have a graph tab that will tell you what services you're running, how many replicates you're running, what pods are running, what tasks are running. And we had to do this because without this, we really couldn't go in and figure out how to debug. And not only how to debug, really what's the scale we are running at. The numbers that come out and you have to go do looking at logs takes phenomenally longer time than for us to go look at something like this and get to an answer quickly. Now, these are all the services that are running already. These are the core services that you saw in the architecture diagram, where this is just the applied AI running and waiting for somebody to issue any commands. And what you see here in this big flower is all our task services. So we have 50 services running, waiting for any of the tasks to come in. Now if I go in here and say AI guided build, and I'm saying use a local file, and saying out of all the different combinations of inputs you can use the top 10 inputs that the model is automatically selecting as to be the most important as a first pass. So this file, the data file, has 1,000 variables. They're all correlated with each other. That's a real data set. And you as a data scientist or a subject matter expert can go in and figure out which variables are important before going and building a model. What I'm asking is go build all possible models for all possible combinations of variables, selecting the first 10 important variables per model. That's what this command would do. Right? Hit enter. What it's doing is it's going off, and in this particular case, it has 200 variables. It's running 1,056 total models. And you can see it's pushing off all of those task runs to the Kubernetes engine. And as soon as the Kubernetes engine gets all of these tasks launched, it'll then send back, and you can see the graph already updating. It's actually faster on the screen here, but each of the color nodes that are coming up, each one of those nodes are actual models that are getting spun up. And as we're speaking, we've already spun up 693 models, and it's live updating as we speak in terms of going off and pushing it to GKE live off of the conference Wi-Fi here. Right. So as we're speaking, we just took a data set, pushed it out without knowing what is actually in there, asking the system going to figure out how many models can you build, what are the combination of inputs that will actually work for each of those models, go build it, and come back to me and show me a result. And all this running live on a system that's live on Google Cloud. And in this particular case, it's now already finished building about 713 models, right? And the responses that you're getting back on the screen there are running live with all of these containers getting spawned off inside the Kubernetes engine with all of the connections between the different services running on the cloud. Okay. Now, can we switch back to the So what just happened here was this data set, where we took this data set with, in this case, 200 different variables with a combination of correlations between them. The plot you see here, each color is a correlation between one variable and another variable, right? The system went in, looked at the correlations, looked at a lot of the other heuristics in the data set, figured out what models to build in a variety of different techniques, ran the models, and came back with an answer for you, right? Now, to run this, the scale of the nodes that ran live in a few minutes was 50 nodes running 4,800 CPUs with about 30 terabytes of RAM. Right? So yes, you just spun it up for about 5 minutes, came back down, but you saved an engineer maybe 2 weeks worth of work. And they can actually go do work on what is more meaningful for them to go ask questions and get answers from, rather than figuring out what is this data set actually telling them, right? And we have a lot of workflows built in internally for us to go get the acceleration of analytics possible internally as well. Now, we did run this on not on Wi-Fi, but actually today morning with a proper internet connection. We could run 30,000 models live, loading up the Kubernetes cluster that I just showed you with about 60% utilization. Okay, and the graph actually looks like that. It went live in about 2.5 minutes, spinning out all the 30,000 models live. The nice thing about this is not all 30,000 actually succeed. A lot of times when you try to push 30,000 models through a cluster that is of this size, a lot of those things fail that have to be restarted automatically, right? And having GKE, having the cloud native services that automatically restart helps us tremendously as well. We didn't have to really worry about the infrastructure at all in this particular case, right? So I just want to leave you with two thoughts. One is we're not experimenting here. We're not really saying this is an abstract thought maybe that'll be available in the future in 5 years' time or something like that. We're saying industry is using this today. A lot of these applications may not seem like traditional deep learning applications, traditional cloud applications, but a lot of these applications are moving to the cloud as we speak today. And a lot of industries are actually embracing it, not necessarily resisting it, right? And challenges still do exist, right? The biggest challenge, of course, is accessibility. So everybody says they have a lot of data, but when you go in and say, can you give me the data sets? That becomes a 6 months to a 1 year exercise. Because internally, they have to go figure out how to go get the data, who has access to these data sets. And the biggest hurdle today really is not even just the data sets or the talent. It's really the changing the mindsets, where everybody wants to do something with analytics, everybody wants to do something with cloud, everybody understands that it's going to be valuable to them. It's about how they contextualize that value to their actual context. That's the biggest hurdle today. So I'll leave you with that. Thanks a lot. Thank you. Thank you. Thanks.